Hello and welcome to another day of Advent of Code. This is day 10, and day 10 definitely ramped up the difficulty, at least on part 2. I thought part 1 was really straightforward, but part 2, I spent over an hour on part 2, so it's pretty complicated. But anyway, I'm here to explain to you how to solve both parts, as well as two solutions to part 2. One that somebody showed me in chat, and like after thinking about it, it was so obvious after thinking about it a bit, but I don't think I would have ever come up with it on my own, but I'm going to show it to you anyway because I think it's a really cool solution. But anyway, the input of our problem today is a list of integers for joltages. And if we open up our parsing, as we usually do, it looks kind of like this. They aren't in any particular order. And the description of the problem is that joltage starts at 0, and the end joltage is the max joltage of any of your adapters plus 3. And so that's what your device target is supposed to be. And you're supposed to connect these adapters together and power your device. Note that adapters can connect to joltages that are less than 1, less than 2, or 3 less than the current joltage. So like if you're going from 0, you can connect to either 1, 2, or 3, for instance. And so given all that information, we're supposed to figure out the number of 3 gaps and the number of 1 gaps. But anyway, let's do the parsing first. The parsing for this is very easy. It is return. I'm actually going to sort the output here because it's going to make it easier to handle later. There's probably, actually, I don't know if there's a solution without sorting, but sorting the output is going to make this a lot easier to handle because we're going to be dealing with the gaps between them. Oh, also another thing to note for part 1 is use all the adapters. I forgot that in the problem description. But anyway, we're going to do return sorted int s for s in, or actually we should say int line for line int s dot, oh my goodness, my typing is all over the place today, for s in split line. So this should parse us here, and if we run this parsing.py, import our type annotations, then you'll see that we parse our list here. Now, when I looked at this list, I noticed a couple of things, and we're actually going to be able to use these facts later. You'll notice that some of the numbers are 3 apart, and some of them are 1 apart. And nowhere in any of the inputs that they gave us were they 2 apart. So we can kind of use that information to simplify our solutions. Now, again, it won't work for all possible cases, but it'll work for every case that they gave us. But anyway, that's the parsing description. So let's actually jump into part 1 now. Open up part1.py. I'm actually going to sort these, and I know my text editor doesn't sort properly, so I'm going to have to resort a little bit manually. It does a non-natural sort. It does a just alphabetical sort, and so the numbers don't work out. But anyway, this is the numbers in order, and that should hopefully help us visualize this. And so for part 1, we're supposed to figure out the number of 3 gaps and the number of 1 gaps between all of these. So if we did this manually, this is a 3 gap, this is a 1 gap, that's a 1 gap, that's a 1 gap, 3, 1, 1, 3, 1, 3. And then there's actually one additional one on the end to get to your actual device itself. So we have to make sure that we count that one. But since we're counting gaps, that's, my brain is immediately jumping to using a counter. So I did a video on counters. I like to do import collections. So I will link that video in the description. And we're going to do counts equals collections.counter. And note here that I'm going to initialize counter to have an initial value for that very last one. So we're going to say that there is already one 3-jump difference here. And the way that I thought about this in my head is I want to look at the current number and compare it to the previous number, subtract the 2, and that'll tell us our gap. And so at the start of our thing, our current number will always be 0. And that's because joltage here starts at 0. And then we're going to loop over every number. So for number in input, and you would use sorted input if your input wasn't sorted, but in my case, it's always sorted here. And we're going to increment the counts of the differences. So we're going to do counts number minus n, this is going to give us our difference, plus equals 1, so that's just an increment. And then we need to set the previous number to our current number, so we're going to say n equals number. And if we run that and look at what we get so far in there, part1.py, we look at our counts, you can see we have 7 1 jumps and 5 3 jumps. And I believe the problem, what did the problem want us to do? It wanted us to return, to multiply those together. So we can do return counts 3 times counts 1. And for this particular small input that they give us, this should give us 35. And if we run that, cool, that all works great. I don't think there were any real tricks for part 1. This was, I think, pretty straightforward. Now, if we look at the overall runtime of this, of course, there's, we did a sort before. And so that is going to be O of n log n, n times log n. And this is going to be O of n. And, building this counter is constant time because there's only going to ever be 3 slots in it. And so overall, the ON doesn't matter in context of n log n, and so the sort is actually dominating our runtime here. So our overall runtime is n log n. But now let's move on to part 2, and part 2 is where things get really, really confusing. So part 2, I'm going to sort these again. Let me do that really quick. Sort, and then fix the sort. That's actually not going to work well over here where the numbers get really big. This is the larger input, which we'll also handle as well. Oh, this is really going to be painful. So let's go down there. I should have set this up before. I'm sorry about this. 20s and then 30s. Oh, I could have saved a few arrow keys there. And then 40s. But anyway, so for part 2, the question is asking us to find all of the combinations, the count of the combinations that the adapters could be arranged in. And so when I saw this problem, I started thinking about, the differences between these and how many combinations you can get when you look at subsets of the problem, trying to break the problem down and think about it in different ways. So you'll notice here that if you have 2 numbers that are 3 apart, there's only one pathway that could go through those 2 numbers. However, if you have, contiguous chunks of 1 apart things, that's where the problem gets interesting. So in this case, there are 3 1 gaps in a row. And so you can see there's one path that just goes through all of them. There's one that skips 5. There's one that skips 6. And then there's one that skips 5 and 6. And so there's actually 4 paths when there are 3 gaps here. And you can see down here, we have 2 1 gaps in a row, and there's only 2 possible paths through this. So there's one through all of them, and then there's one that skips 11. And I started thinking about that, and if you took, the number of paths here, so there's 2 paths through this, and there's 4 paths through this, and if you multiply those together, you'll get the total number of paths through everything, because it's basically every combination of them. And so just thinking about the first input, the answer is 8, but how do I represent that in code? And how do I generalize that to larger segments of things? And so what I did is I started drawing this out, and spoilers at the bottom, but I started drawing this out. And so when there were 0 1 gaps in a row, there was 1 combination out. When there was 1 gap in a row, you still have 1 combination. There's no other way to traverse this. But as soon as you get to 2, now there's 2 paths. I've tried to represent the different paths as colors. So the blue path is always, or the light blue path is always the straight through path. But you can see we jump over 4 in this case, and so that gives us 2 combinations. As soon as we have 3 1 gaps in a row, there's a bunch more combinations. So you can jump over 4, you can jump over 4 and 5, you can jump over 5, and you can go straight through it. That's 4 combinations, and et cetera, et cetera. You can keep building these out. After 4, it gets way more complicated. There are actually 7 different paths that I've drawn here. But getting to 4 was enough that I needed to see kind of a pattern here. And the pattern that I saw was, if you take any number and, well, let's take this one. We take 4. If you add the 3 previous numbers, you're going to get that value. So to get 4, you added 2, 1, and 1, and you get 4. To get 7, you added 4, 2, and 1, and you get 7. And that's kind of the pattern that I built up. This actually looks a lot like Fibonacci, and in chat we called this the Tribonacci. I think there is actually a sequence called Tribonacci, and it is this sequence. But anyway, this is how I generalized this form here. And we're going to use this thing to do our one solution. This is, I think, actually the more complicated solution, but a lot more intuitive to me. I'll show you the simpler solution in a bit as well. Okay, so in order to compute kind of this thing here, I decided to make a function for this, and we're going to use, let's see, from typing import list, we're going to implement basically our own Fibonacci, but instead it's going to be Tribonacci. And we're going to do that by minimizing our result, because normally when you compute Fibonacci, you don't have to recompute all of the smaller ones, and if you do it naively, you spend a whole bunch of time recursing and computing those. But we're gonna simplify this a little bit and use functools.cache. Well, cache is in Python 3.9 if you just want to always cache it, but we're going to use functools.LRU cache and max size equals none. That way it grows unbounded. I did a video on LRU cache, so I will link that in the description as well. And I'm going to call this combinations per streak. And we're going to give our streak an n. That should not be a str, it should be an int. And it should return an integer. Now, in this case, we have to define some of our base cases so that we can get out to larger numbers. And I'm going to do that with just these three cases here. So if n is equal to 0, return 1. Elif n is equal to 1, we also return 1. Elif n is equal to 2, return 2. And so those are our three base cases here. And then for the generalized case, after this, we can say else return... we're going to make this function name shorter. We're just going to call it comms. Return comms n-1 plus comms n-2 plus comms n-3. So that'll give us our three previous numbers. So if we pass 3 in here, we'll get comms of 2 plus comms of 1 plus comms of 0, which will be 1 plus 1 plus 2, or 4. And so that's kind of our comms function. Just to validate that, I'm going to print all those out here just so we can see that. Print... Let's see, comms I, and I'm going to use the trailing equal here, which is a Python 3.8 feature to debug f strings. Python 3 part 2.py. And you can see we get our 1, 1. Oh, I forgot to... Oh, that's annoying. I guess we'll put the I in there as well so that you can see there. So you can see from 0 to 1, 1, 1, 2, 2, 3, 4, 4, 7. And you can actually generalize this out to any number that you want, and you can see like how it grows. In our actual problem and the input that they give us, I think it only goes up to 5 in a row, maybe 6 in a row. I'm not really sure. But, you know, computing this function will help us the rest of this time. The way that I actually did this when I did this live is I generated all possible subsets and then just looked at the length of them that satisfied the conditions. But then I drew this nice diagram for you for the video. But anyway, let's get rid of that. So now we need to figure out the streaks here and multiply those, you know, each streak count together to get our final number. At least that's one way that I'm going to do this. So if we take our input here, the way I'm going to keep track of streaks, we're going to start at a streak of 0. And we need previous number at 0 as well. And actually, we can just say the previous is going to be input 0. I'm actually intentionally making a bug here so that you can see how I fixed it when I was debugging this live. And maybe you'll make the same mistake, and I can, you know, use this as a hint as well. And so what we're going to do here is, oh, we also need our end, our end total. We know that the total can be 1, like at worst it's 1, and we're going to be multiplying against this total using this function here. So picking 1 as my multiplicand is helpful there. If we pick 0 here, we just 0 times anything is still 0, so it's not super useful to build up this, this chained multiplication. But anyway, then we can do for number in input 1 : so took the first number and then the rest of them. And we can basically say, like, if we're in a streak, if the number is, you know, previous plus 1, we will increment our streak. So if number is equal to priv plus 1, then our streak continues. Otherwise, if we have otherwise we want to multiply onto our total whatever our streak is. So we can do total times equals comms of that streak. This will allow us to multiply out. Now note, even if streak is 0 here, we're still going to be multiplying 1 by 1, so this is completely okay. And if we ever break our streak, we need to reset our streak back to 0. And if we run this, I don't think this actually works correctly for the first problem. Let's see what happens when we return total here. Syntax error, I forgot to colon. Okay, yeah, we returned out 1 here, and the reason we didn't do this properly... actually, let's print this whenever we do this. Print streak. Just to show when we're multiplying in here. So we did a lot of multiplying by streak 0. Oh, I see what we forgot to do. We forgot to reassign previous here. So we gotta say prev equals number. Okay, and now we're getting 8 for this one up here. Let's actually comment this out down here. And let's, instead of inputting, or, oh, I see what we did here. We should not be using the global variable here. Let's use this local variable because we're going to be looking at different combinations here. So we're going to look at LST here. But anyway, we actually have the first problem working right now, and that's great. But let's try our second input down here. This input has a couple of different characteristics that make the problem a little bit harder. And we'll talk about those in a second. But if we run this now, we actually get the wrong value. We get a very, very wrong value. We get 1,568. And part of the reason for that is we actually end our puzzle on a streak here. And so if we look at our, after our for loop here, we still have a streak. So if we do, you know, after streak equals, you'll see that we still have a streak of 4 here. So we need to make sure that we multiply that streak onto our total as well. And so you're going to do total times equals comms for streak. And that should get us closer to the problem. Oops, what did I just do? I meant to put this here. That should get us closer to our answer, but we actually get this super cursed number, 10,976. I was stuck on this for almost an hour. But I'm going to show you the little hint here. So we solved the end of the problem, but we failed to solve the beginning of the problem. And the reason for this is actually I tried to make a little bit of a shortcut here, and it actually ended up biting me. So the problem here is we're actually not considering our first number, even though there's actually a jump there. And so we could be increasing our streak length based on that. So if we looked at the short input, we weren't ever, having a streak at the beginning, so it wasn't ever wasn't ever useful. But at the beginning of this input, we start a streak, and so our streak is actually off by 1 here. And so we need to, like, the trivial solution to solving this particular, keeping most of this code the same, is to insert 0 at the beginning. So I could do list.insert 0, 0. This, of course, modifies our input, so it's maybe not the best. And you can see now we get the expected value here. But probably a better way is to not actually do this here and just say prev equals 0 and loop over every number in the list. And that'll also give us this answer here. So this is how I solved the problem. But someone else showed me another clever way to think about this problem. So this does work, and it works for both of those inputs. And I'm going to show you another solution that's more clever. Compute clever. List int return int. So the way that some other people thought about this problem is if you're at a point in your list, how do you get to that point? And so the answer is you could either come from -1, -2, or -3, and you can kind of, generalize that back to the original part of your array. And, to get to 0, you have to be at 1 path. And adding up all of the previous paths can get you there. So let me show you the solution that they came up with. And I'll kind of explain like how that works intuitively. It avoids any of this like special thinking about combinations or like having to figure out streaks. It just simply adds up the previous values. And so basically what they did is they kept a mapping of how many steps or how many combinations it took to get to a particular part. And so they had combinations equals collections.defaultDict of int. And you can seed this value by saying you got to 0 by taking 1 step. So like there's only 1 combination that could happen at 0. And then you want to loop over all of your numbers. And again, they're sorted, so you would still have to sort here. And I'll talk about algorithmic efficiency for both these in a sec. So they start sorted, and so you would loop over each number for number in list and figure out how you got to that particular number. The combinations that could get there are the addition of all of the previous numbers that could reach there. So -1, -2, and -3. So you can say the combinations number equals We're actually going to make this shorter variable name as well. Combinations number equals comms number minus 1 plus comms number minus 2 plus comms number minus 3. We're going to replace the word number with n just because that way it fits better. So basically, you know, the number of paths to get to the previous value, the number of paths to get to the one that's 2 away, and the number of paths to get to the one that's 3 away. And we actually abuse a neat little property of default dict, and I did a video on default dict, so I will link that in the description as well. When you access a value that's not in the default dict, it will default initialize it, that's where the name comes from, with the callable in the first thing. So int pren is going to give you 0. So if you ever access a key that doesn't exist, you're always going to get 0. So even for the first number that we're looking at, so when we're looking at, you know, this 1 up here, we're going to try and access the combinations of 0, -1, and -2. These are both going to be 0, but this will be 1. And, you know, extrapolating this out through the rest of your list, you eventually get all of this computed and all adds up nicely. And if we look at the last value of our list, which should be the number at the very end, let's see, LST -1, that'll tell us how many paths that could reach that value there. And if we take these and do compute clever on both of them, oops, what did I just do? You'll see that that one also gives us the right answer there, part2.py. Of course, if I can match my parentheses properly and import collections, that's what you get for live demos. Compute. Compute clever, there we go. And you can see that that also answers the question. But, you know, much shorter, a lot simpler, but I don't think I would have ever thought of this solution on my own, so kind of cool. But anyway, let's talk about the algorithmic efficiency for all three of these things here. So first, let's talk about this combinations function. And the neat thing about this is it's actually constant time to do any of these. I mean, at worst case, you can kind of think it as being linear, but there's no logic happening for any of these. And because of this caching, we only ever look up 3 values in a ON or O1 lookup here. So these are all O1 operations, even though we're doing it 3 times. And so, you know, without this decorator here, it's actually, I think, n factorial? That might be 2 to the n. I don't know. It's very slow runtime without the caching, but extremely fast with the caching. So this is kind of a neat little, I don't know, the word is dynamic programming for this, but I don't know, dynamic programming is just a schnoozy word for caching. But anyway, so this is O1, essentially. O1 because we're caching stuff. So we don't really have to worry about the runtime of that. And if we look at compute part 2, again, we still have that sneaky sort here. So we're still looking at n, O of n log n here. So there's still that sort there. And then this is just, you know, O n. Now, multiplication actually doesn't happen in linear time, but you can kind of think of it as constant time. Or sorry, it doesn't happen in constant time, but you can kind of think of it that way relative to looping through a list. So this loop here is O(n), but it doesn't matter because, you know, this is still dominated by the n log n sort. So overall, n log n for this form of part 2. And if we do the same thing down here, this is also n O of n log n, because we have that sort there. And this is still O(n) here. Though we have, let's see, we have additional, you know, order n space here. So this one is also n log n, and not more complicated than that. But anyway, those are kind of the 2 solutions that I thought were the most important to show you all. This is the one that I figured out and how I figured it out. And so hopefully, you know, this diagram and this solution can help you. But thank you all for watching. I'll see you for the next day. Peace.